Uh, Hello, everyone. We are very happy to have Professor Yuval Gefen here today, who will tell us about weak measurements, a peephole into the quantum world. Professor Yuval Gefen is visiting from Weizmann Institute, and in fact, he did his PhD in 1983 with Professors Imri and Ahroni, and in fact, they started the field of mesoscopic physics. And after a postdoctoral fellowship with Professor Thaulis in the US, he came back to Weizmann in 1986, and he's been there ever since. He's got many awards, which I'll not mention. There's the Wolf Prize, the Max Planck Research Award, and so on, and many fellowships of various societies and so on, which again, I'm not going to mention. But I just wanted to mention that he's been associated with India for the last 20 years, and has trained many postdoctoral fellows, Indian postdoctoral fellows who are now in different institutes in the country. He's also organized several, co-organized several workshops and conferences here. And he's currently Infosys visiting professor at Indian Institute of Science in Bangalore itself. With that,
yeah. Thank you very much, Sumati, for the presentation, and thank you for inviting me here. I'm delighted to see familiar faces, including two of my collaborators, Sumati and Stitadi. It has been some time since I have been here last, almost 4 days, so it's a great feel coming back again. What I'm going to tell you today is a sort of a journey from the very first foundations of quantum mechanics all the way to some present-day quantum information protocols. This is a partial list of some of my main collaborators in this direction, and I'm particularly delighted to have been collaborating with experimental groups over a broad range of platforms, Keter Murch on superconducting qubits, Ibrahim Karimi on quantum optics, and Roy Ozeri on the cold ions. So I'm walking on the street in Tel Aviv one of those days, and an acquaintance of mine, whom I haven't seen for years, comes across me and says, "Hey Yuval, how are you? We have not seen each other for years. I heard you are doing quantum mechanics. Can you tell me what quantum mechanics is all about? But I have only 2 minutes to spare." And I take the challenge, and here is quantum mechanics in 2 minutes. It stands on 3 pillars. The first pillar is a wave equation. Waves are particles, particles are waves. The second one is non-locality on the level of a single particle. And the third one is a non-locality on the level of 2 or more particles, which includes entanglement, topological excitations, and quantum statistics. So fermions, bosons, anyons, non-abelian anyons. So this takes me back to the very early days of quantum mechanics. This is arguably the most celebrated group photo in the history of physics. Of the 29 faces here, 17 are or to be Nobel Prize laureates. Now, this 1 week Solvay Congress, at that time, they didn't use the word workshop or conference, they used the word Congress, which the 1 week Congress featured the battle of titans between Niels Bohr representing the younger group of the guys who were responsible for the breakthrough of quantum mechanics, and on the other side, Albert Einstein. Every evening of that conference concluded with Einstein standing and bringing yet another insight, another question, another paradox that he sees in quantum mechanics. And in the morning, Niels Bohr will stand and explain out, or in his opinion, explain out why Einstein's worries were trivial or wrong or non-existent. One of those paradoxes became known as Einstein box paradox. And the idea was very simple. In our eyes, it's trivial, but in the eyes of those guys, it was highly non-trivial. We take a single particle in a box, the wave function fills out the box. We cut the box adiabatically into two. We send one part to Paris, the other part to Tokyo. According to quantum mechanics, the wave function still fills the two parts of the box. And now we perform a measurement in Paris. If we find that the particle is there in Paris, then in no time, the wave function evaporates from that part in Tokyo, and vice versa. If we find that the box in Paris is empty, then immediately the particle establishes itself completely in the box in Tokyo. So Einstein has concluded that quantum mechanics is either non-local, because we do something in Paris and immediately, in no time, something happens in Tokyo, or incomplete. That is, somehow, when we cut the box, the particle managed to sneak into the part of Paris, and this is why we find it eventually in Paris. To the eyes and ears of the other participants, it sounded like a complete nonsense. Einstein was complaining bitterly about Niels Bohr in the letter 1935 letter to Schrödinger. He complains and says that this Talmudic philosopher Bohr doesn't give a hoot for reality. But back during the end of this Solvay Congress, Paul Ehrenfest, who was a very good friend of Einstein, stood up and said publicly, "Einstein, I'm ashamed for you." So much was the appreciation for Einstein observation. But then years later, Heisenberg, who was a young guy at the time, writes in his notebook that he is still thinking about Einstein paradoxes and about this box paradox. He doesn't know the solution, but he would prefer, he uses the word prefer because it doesn't have any proof, to believe that quantum mechanics is complete but non-local rather than the other way around. Now, part of it, I mean, we all know that it took till the mid-1980s to show this feature of non-locality of quantum mechanics. Einstein was right. So part of this Gedanken experiment with the box involves a measurement. We want to see whether the particle is in Paris or in Tokyo. And what we can see is that in this measurement, which we call today a strong measurement or projective measurement, is associated with the reduction of the wave function. What do I mean? Here is John von Neumann, who later put all this in mathematical framework. So John von Neumann established or postulated that evolution of quantum systems comprises two different paradigms: continuous evolution, unitary evolution, given a certain Hamiltonian, and then collapse due to some measurements. So if we have a system in a state psi, and John von Neumann performs a stronger projective measurement of a certain observable, then immediately the system collapses onto an eigenstate of the operator which represents this observable. Or another demonstration, here we have two figures, Philip IV, the King of Spain, and Mark Zuckerberg. And what I'm going to show is to create is a superposition of these two, and then perform a measurement. So here we go. This is a superposition. We perform a measurement, and I projected onto Zuckerberg. Let me, those who missed this, let me repeat it again. A superposition, I perform a measurement, and oops, this time it turned out to be Philip IV. So this demonstrates the stochastic element of this projective measurement. By contrast, generalized or weak measurement refers to getting some information from the system, but a blurred, noisy information. So here is John von Neumann hearing a knock on the door. He is looking through the peephole and sees some figure, but he cannot even tell whether this figure is a male or female, and whether the figure faces him or with the back to him. So there is certain information, but not complete information that we can extract. The advantage, the big advantage here, is that this figure doesn't know, this person on the other side of the door is not aware of the fact that he or she are being measured. So we do not perturb the system, or we minimally perturb the system. To use a more physical example, let us take a double quantum dots. These are two pieces of metal or a semiconductor connected by some tunneling bridge, and we put one electron on this system. So the Hilbert space of this system is spanned by electron is on the right and electron is on the left. Of course, we can have superposition. This is our detector, our measurement device. In the jargon, it's called quantum point contact. It's a conductor with a constriction here. We inject current I here. Some of the electrons will be backscattered. Some of the electrons will go straight. And with this device, we want to measure what the state of the system is. So we perform the measurement over a time delta t. We integrate over the current that manages to go to the other side, or in other words, to the total charge that managed to flow to the other side. And the probability distribution here is bimodal. It's this peak if the electron is on the right, the other peak if the electron is on the left. And we know that if we measure that particular value of Q, then with all probability, the system was in the state left. Let us now go to the limit of weak measurement. So weak measurement, we reduce the coupling between the system and the detector by moving the detector further away, or by reducing the time of the measurement. So the distribution function of Q is still bimodal, but these two partial distributions now overlap. Again, depending on whether electron on the right or on the left, we have this peak or the other. But if we measure this value of Q, our statement now is probabilistic. It is more likely that the electron was on the right than on the left, but we cannot tell for sure. Let's take a caricature of this caricature and take again our system where the electron is in the superposition of left and right, performing Rabi oscillations. And we now consider, instead of impinging current, a single electron that impinges, and this electron can either backscatter or be transmitted. And now let's assume an extreme case. If the system, the double dot, is in the state right, the electron for sure will be reflected. If the system on the left, the electron for sure will be transmitted. So we can write down a 2x2 table. If the state of the system is right, the resulting state of this scattering experiment will be fully reflected. If the system is in the state chi1, which is left, the scattering state will be fully transmitted. So following the injection of the electron into this quantum point contact, we obtain an entangled state of the system and the detector, the electron in the detector, which can be written as an external product of chi naught times phi naught plus chi1 times phi 1. Now, this state reflects perfect entanglement because phi naught and phi 1 are orthogonal. They have a zero overlap. So initially, we took a system which was in the superposition of chi naught plus chi 1. But after performing a measurement following this scattering experiment and realizing that the electron was fully reflected, we project the system onto the state chi naught. In other words, knowing that the electron was fully reflected gives us full information about the state of the system. The system was in chi naught. Let's try to repeat this logic for a weak measurement. In that case, whereas strong measurement or projective measurement was associated with a perfect entanglement, strong entanglement, here weak measurement is associated with weak entanglement. Let's see how it goes. So we have again the electron on double dot in our detector, and now we send one electron, we inject one electron from here, and this electron has a probability amplitude R to be reflected, probability amplitude T to be transmitted. Now, if the system is in the state left, and assuming the interaction between the detector and the system is weak, the measurement is weak, these amplitudes will slightly be modified. Instead of R and T, we have R plus delta R and T plus delta T. So here is our 2x2 table. If the system is in the state chi naught, which is right, the scattering state will be R times reflected state plus T, amplitude T times transmitted state. And if the system is in the state left, these amplitudes will be slightly modified. So we can still write the state of the universe, the system and detector, in this way, chi naught times phi naught plus chi 1 times phi 1. But this is not a ideal entanglement because phi naught and phi 1 have a finite overlap. Actually, if we put this detector on the moon, there will be no interaction between it and the system. And then the scattering state of the detector will not care whether the system is in the state left or right. So the resulting state will be the state of the system times the state of the detector, a product state. There will be no entanglement whatsoever. So if, for example, we find out that the electron was reflected, it can indicate that the system was in the state right or in the state left. There will be different probabilities that we will be able to determine probabilistically whether it's more likely that the system is in the state right or left, but we will not be able for sure to tell which state the system is in. So what we have learned so far about measurement, quantum measurement comprises 3 steps. The first step was that we coupled the system to the detector and let them evolve in a unitary manner, employing a system detector Hamiltonian. If the coupling is weak, then we refer to it as the weak measurement. Following this interaction, the system and the detector become entangled, weakly or strongly, depends on the strength of the interaction. After time, delta t, the time of the interaction, we decouple the system and the detector. And now we look at the detector, which is now decoupled from the system. And on this detector, we perform a projective measurement. So regardless of whether the interaction between the detector and the system was weak or strong, at the end of the day, the readout of the detector is always strong. So we project the detector in a certain direction. So that's these are the 3 steps of quantum measurements. But now I'm going to argue that the mere fact that we read the detector implies some back action on the system. This is the result of a non-local influence of measurement of the detector on the system. This is a manifestation of the non-locality of the system. Let me elaborate. If we perform, yeah.
I have a short question about this detector and reading. So the fact that the detector is in a readable state, okay, this left and right that you were pointing out, does that
The detector or the system?
The detector.
Yeah.
Okay. The fact that the final state of the detector is readable in terms of variable, does that assume the class of systems that we can use as a detector? Or does that constrain the kind of systems that we use as a detector?
Not really. I mean, the examples I'm going to use will be that of a detector, which is a spin half or a qubit with 2 discrete states. But I can easily generalize this theory to a detector with a continuous spectrum of eigenvalues, a continuous dial. It will be just easier for me pedagogically to restrict to talk about a discrete 2-state detector. So let me distinguish between classical measurement and quantum measurement. So classical measurement may or may not result in a back action on the system. For example, I stand at on the side of a highway, taking the speed of a passing car, and the driver in the car will have no idea that I took his or her speed until they get a speeding ticket home. So this is an example of no back action of my measurement on the object. But I can have an example of a friend of mine that comes and tells me, Yuval, I suspect that I have some gas leakage for my car. Can you make some classical measurement and tell me whether the car is leaking or not? And I tell him, yes, of course. I approach the car, take my matchbox, light the match, and if the car explodes, I know that there was a gas leakage. So there may or may not be some back action. With quantum system, the measurement must result in a back action on the system, which sounds like bad news, because ideally I would like to perform measurement that gives me information on the system, but does not perturb the system. But here we are. This is quantum mechanics. So the question is whether this is really bad news, or perhaps we can harness this back action for something good. And the something good here will be that we can design the measurement such that the back action will manifest as a nudge on the state of the system. We repeat it again and again and again until we steer the system towards a desired target state. We engineer a quantum state. So why do we want it all to? Yeah.
Simple question. If the back reaction is too large, will it not change the system to the extent that what you wanted to measure cannot be measured?
Right. I mean, for example, it's a question of what I want to measure. I mean, suppose I have a spin half pointing in this direction, and I want to measure the SZ component. So if I perform a very strong projective measurement, with certain probability, I will project it to the North Pole, certain probability to the South Pole, and I can, if I repeat it and collect data, I can obtain probabilities. And then I have some idea about the latitude, not about the state, but the latitude on Bloch sphere where this spin was pointing. But you're right. I mean, I'm very limited in the information I collect, and unless I do something more sophisticated. So why do we want to use this crazy and complicated quantum back action to engineer a state? I mean, there are other possibilities. For example, the projection I just mentioned. So suppose I have a spin half and I want to project it in the direction of the North Pole. So I can project it, and the success of my experiment is probabilistic. Sometimes I will manage, sometimes I will end up in the opposite direction. Not good. The other thing, I can take a system which is subject to Hamiltonian. I can define my desired state as the ground state of this Hamiltonian. And now I introduce some very minute thermal contact to a reservoir, which is essentially at zero temperature. I cool the system, and then the system will reach the ground state. The problem with that is that if the system becomes complicated with many degrees of freedom, the gap between the ground state and the next states may become exceedingly small. I don't want to argue here whether it will be algebraic or exponential. We can argue about that. But the temperature I need to cool my reservoir to becomes practically inaccessible. And the other option is, suppose I'm back to my spin half. It points in this direction. I want to prepare it in the direction of pointing in the North Pole. I apply a perpendicular magnetic field at the right magnitude for the right time. The spin rotates, and here I am. The difficulty here is, first of all, I need to know what my initial state here with high accuracy. Second, I need to really control the strength and the time I apply this field. Otherwise, I will end up overshooting. So this is our a very greedy wish list from quantum state engineering. We want to steer towards a desired target state. We want to start with an arbitrary, at least unknown to us, initial state. We want the protocol to be relatively robust against any perturbation on the way. We want a protocol where we don't need to control precisely the time over which we apply this protocol. If we apply it and we went to have lunch and we came back, we want the system still to be stabilized. And lastly, the target state needs not be a ground state of a Hamiltonian that is known to us. And this is indeed the wish list that we want to satisfy when we come to our quantum steering. So here are the steps that we exercise. The detector qubits are prepared in an initial given state. A single qubit or many detectors, many qubits. So we prepare them in a state which we decide upon, and these states are completely independent on the running state of the system. We couple the system to the detector, let them evolve in a unitary manner. So the density matrix of the system and detector at time t plus delta t is given by the unitary evolution with the system detector Hamiltonian of the initial product state. This is the density matrix of the detector, which is initialized in a given state, and the running density matrix of the system. So we do this step, and then we repeat this state, and repeat each time we initialize our detector. The question is, once we perform one step like that, what do we do with the detector? And here there are three paradigms. One paradigm is that we don't look at the detector at all. Actually, we throw away the detector and take another one. So mathematically, this will amount to a tracing out over all possible results of readouts of the detector, and then reinitializing the detector and starting again. We call this a blind steering, and this blind steering is an example of passive steering. Passive steering is a protocol where we decided on the step of the protocol, how the step of the protocol will look like, regardless of what the actual readout from our measurements are. So this is the blind steering. There are two other paradigms, possible paradigms. One paradigm is that we do some steering, and only if the outcome is something of our desire, we post-select this result and we'll continue. I'm not going to talk about it. It has some very interesting physics. The third paradigm, which I will talk about, is a smart paradigm where our steering protocol at a given step relies on and derives from the history of the previous readouts. But let us first stay with the passive blind steering. And I give you an example. The example here is a model in quantum condensed matter, which is called the AKLT. This is a model of a chain of spin 1. The Hamiltonian is given here. L is the lattice point. And here I take a chain with periodic boundary conditions. I can rewrite the Hamiltonian in terms of projective operators on a link. Link means two neighboring spins, where I project on a sector of total angular momentum equals 2. I have two spins of spin 1. The total angular momentum can be 2, 1, or 0. So I project onto the component of 2. Now, each of these terms is non-negative. So clearly, the ground state of this Hamiltonian needs to be a state where each bond, each pair of neighboring spins, has 0 weight in the total spin equals 2. So that's the ground state of the AKLT model. I'm not going in this colloquium into details how I do it, what kind of system detector Hamiltonian I do, but let me just show you some results. So this is our chain. We want to have a set of detectors. Each detector, we want it to be local. We want it to be coupled to a set of neighboring spins, for example, a pair of spins. We request that the complexity of the system detector Hamiltonian does not increase with the number of spins with the length of the chain. And we want the number of detectors to be not more than proportional to n, not more than extensive. And with this, we managed to define a system detector Hamiltonian, repeated these steps, and the measures how the distance between the running density matrix, and the density matrix of the target state, the ground state of the AKLT model, behaves with time. Time is measured in terms of a number of measurements. We can use this measure of distance for Binius norm or trace norm, but you see that in either case, the distance to the target state decreases exponentially. Success. So this here I gave you the flavor of a passive steering, and now I want to move to something which is much more efficient and interesting, which will be smart active steering. So what did we have so far? With the blind or passive steering, in each step, we had a product of the running state of the system times the initialized detector. We let them evolve with the unitary evolution. If the detector has 2 states, we perform a measurement, and these 2 states are 0 and 1. We trace over the detector. This tracing, will have back action of the system, and then we reinitialize the detector in the same state, and we repeat this again, again, and again. When it comes to active feedback, we have 2 additional ingredients in this protocol. And the 2 additional ingredients are, first of all, we take note of the history of the readout. We keep a trace of the readouts, which will be some vector of 1, 0, 0, 1, 0, etc. The second ingredient is that we need to use this history vector of the readouts, in order to decide what would be the new system detector unitary operator, such that we improve the protocol, such that we improve the runtime, and we improve the fidelity, the overlap with our target state. And for this, in order to define such an active protocol, we need 2 elements. First of all, we need to have a set of system detector Hamiltonians. I call these members of the set alpha. And 2 members of this set are not related to each other trivially, so they are non-commuting. These system detector Hamiltonians can be used to define an evolution operator. And element number 2, we need a policy of how to go from a readout history to a choice selection of a member in this possible set of evolution operators. What we have found out were 2 paradigmatic policies of that. The first policy we called quantum compacts, or cost function policy. So the idea is this. We have our running density matrix, and we define a global cost function. We want this cost function to be minimized during the protocol. For example, we can define an infidelity cost function for the running density matrix and for the desired target state. And we define it as 1 minus the matrix element of the running density matrix with the target state. If we arrived in the target state, then we have 1 minus 1, it's 0. Otherwise, it's positive. And our ambitious goal is to have a set of possible system detector Hamiltonians or possible unitary Hamiltonians, and choose a sequence of these Hamiltonians such that we reach the target state in the fastest and fastest way. This is too ambitious because I need to have a global overview of space and time. So I'm replacing it by a more modest greedy version, which is the analog of steepest descent. I want in each step to have the best, the largest reduction in my cost function. Hopefully, I will get to the target state fast.
So now you're keeping track of the record of the measurements, right?
Yes, I need to have a classical computer on which I have a record of the measurement, and I need to keep track of where I am.
So then it's no longer blind.
Then
it's no longer blind measurements, right?
It's not longer. This is a completely different paradigm. It's not longer. I take particular stochastic sequence, and my ambition is that whatever the stochastic measurement is, in some cases I can go this way. In other cases I can take another trajectory in Hilbert space. But I want all these trajectories to end up in the same desired target state, and I want the expectation value of all these trajectories to be the shortest if I'm there.
So now in this protocol, you are looking at the quantum trajectories, but you are still minimizing the cost function with respect to the density matrix.
With the running then, okay. It depends very much on what you do. If you started with a pure state, then the running density matrix will be a running density matrix of a pure state. If you started with a mixed state, it will be a mixed state. I mean, this is very general, but it could be. But if you started with a pure state, it will be a particular density matrix, which will be different if I follow this trajectory, or it turns out that the trajectory was a different trajectory. Okay, so
here when you say trajectory, you mean, so when you say trajectory, here you mean the measurement outcomes and the active decision making that you do.
Yes, yeah, absolutely. Okay, so this is my AKLT state. I show you results for a 5-spin chain, but we have results for 6 and some statistics on 7 even. So this histogram relates to the blind passive measurement. This tells you how many steps you need, what is the runtime measured in number of measurement steps, in order to reach a state which has an overlap of at least 99% with the target state, fidelity of 99%. Now I'm going to show you a histogram where I do the active decision making. And look at that. Look.
The target space is any state. It's chosen at random.
Here, in principle, yes, but here I chose the target state to be the ground state of the AKLT Hamiltonian, that particular Hamiltonian. Look at the difference in the scale. I have here an improvement by almost an order of magnitude, and when I go to 6 and 7, it becomes more than an order of magnitude. The ratio between the runtime of the passive and active seems to be improving. And this is when I put the two histograms on a logarithmic scale. So it seems to be working, but there is one big caution. And the caution is demonstrated in the following way. Consider a trivial problem. I had an initial state, which was a product state, 1, 1, 1, 1, 1, spin up, 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 and the target set is 0, 0, 0. I use here the language of quantum information, but 0, 0 is down, 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 down. I want to go from 1, 1, 1 to 0, 0, 0. So let's say that I found some protocol that takes me from 1, 1, 1, 1 to 1, 0, 0, 1, 1 to 1, 0, 0, 1, 0, etc. Now, clearly, you look at that and you say, well, it's working. I get closer and closer to 0, 0, 0. But if I'm using my global cost function, each of these intermediate states is orthogonal to the target state. So the cost function is completely flat, has a flat landscape. It doesn't tell me that I'm getting closer. This is, if you think about it more, a relative, maybe first cousin of Anderson orthogonality catastrophe. In order to overcome that, I will need to replace a global cost function by local cost function. I define a reduced density matrix of some segment of my system. I define a reduced density matrix of a segment of the system concerning the target state, and I compare the distance between the two. And with this, this sequence using local cost functions will tell me that indeed I'm getting there. So I mentioned that this is one paradigm. There is another paradigm. The other paradigm is the quantum state machine. I'm just flashing at you an image without explaining. What I do here, I represent the Hilbert space by these circles, by these vortices, and each of my unitary evolutions gives me a colored graph which connects some of those states, some of those vortices. The connection can be multiply connected, can be difficult. So I have a set of possible system detector Hamiltonians, a set of certain unitary evolutions, and each of them will give me a graph, different graph, which is represented by different color. So what I need to do is to take my initial state, identify my final state, and find a multicolored graph that will represent the best score for me, the fastest score to get from that to that. I don't give you any details, but it works. So I'm almost at the end of my talk. I want to mention two, in my opinion, very exciting directions that are presently emerging. One is that the use of active steering is justified not only to make passive steering more efficient, faster. By using active smart steering, I can steer towards states which are prohibited by passive steering. I can steer the unsteerable. I can steer those states which are passively unsteerable. That's one thing. And the other direction is that I can use this idea of steering for quantum cooling and quantum annealing, which are foundational ingredients of a quantum information protocol. So coming back to our hero from the beginning of the talk, Werner Heisenberg, shortly after the emergence of quantum theory, Werner Heisenberg wrote, the conception of objective reality has thus evaporated into the transparent clarity of mathematics that represents no longer the behavior of particles, but rather our knowledge of this behavior, referring essentially to measurement. We measure what we measure, but we modify the state, as was commented here. And the idea is that by employing weak measurement, we get closer to measuring quantum reality. And this is the end. Thank you.
Questions?
Yeah, so I mean, I didn't understand how, like, so after you make the measurement and then compute the distance, right, to the target, and then you said you modify the Hamiltonian, the system detector Hamiltonian in some, but so, I mean, how exactly do you do that?
Okay, so you're talking about the active state. Yeah. So I have a set. It can be a huge set of possible Hamiltonians. And remember that I always want them to be local, connected to a finite number of spins, for example, not to the whole system. So let's say that I followed with my system what is the state of the system right now. So I'm asking myself, suppose I use system detector Hamiltonian number 1. I use the unitary evolution number 1. It can have several different outcomes. I can calculate what is the probability of each outcome, and by how much this outcome is going to improve or maybe make worse my cost function. And I take the weighted average of that. Now I go to Hamiltonian number 2 and so on. And once I do it for all possible candidates, I choose the candidate where the expectation value of the improvement is the best, which doesn't mean necessarily that I improve. It can be unlucky and unimproved. Actually, sometimes there are problems where we identified we needed also to introduce some noise to the system. Sometimes I want to go against my logic, make things a bit worse, because it may happen that the system may get stuck in some illusionary minimum, which I don't want to be there. But that's the idea behind this.
So you probably explained this in your talk, but I missed it. When you define the reduced density matrix, do you actually get a cost function which has an extremum?
Do I actually get?
See, to avoid the orthogonality problem, you traced over some density matrices. I mean, if you go back to that.
Okay. So I have this chain with many degrees of freedom. Mm-hmm. And if I take my global cost function, which was psi target, the running state of the system, psi target, I can be undermined by Anderson orthogonality like events. So what I do the following. I take a segment. The size of the segment is negotiable, like this one. I trace out over all other degrees of freedom, and I obtain here a reduced density matrix, a reduced running density matrix associated with this segment. Now I go to my target state. This is for the running state. And I have a rho as, let's call this segment segment Li of Li. Then I take my target state, which defines also a density matrix of pure state. And I take the same segment and I trace out everything. So I get my reduced density matrix of the target state. Rho as target of the same segment Li. And now I define a cost function which will be sum over all segments of something like a rho, trace of rho running of Li minus rho as target Li square or not square. I mean, we use some measure, but I add up the cost from all reduced density matrix, and that will do the work. That will guarantee that I avoid global Anderson orthogonal catastrophe. And you can even understand it because the orthogonal catastrophe tells you that there is some anomalous power which which is effective when the length becomes very large. But if I a priori limit the length to finite size links, I don't encounter this orthogonal catastrophe.
Thank you. So, so this works then for irrespective of the kind of target state that you want to choose, or you want to go into. The time, it's the scaling of this active steering.
Yeah. So sorry. So what is the question? Is there a limit to this?
No. So the target state that you choose, okay, you showed this scaling of the active steering. So that scaling does not depend upon the kind of state that you choose as a target?
Yes, I don't have a general theory. Look, what we did in order to demonstrate with study for the passive and now for the active, we have, for the active, for example, we have taken a number of test cases. I think for the active, we had something like 4 or 5 qualitatively different states. And we tried it. Now, clearly, the details, the numbers are not universal. Each one is a story on itself. So we are very far from having some universal. But what I want to say is that there is a mathematical theorem now, which for passive steering tells you which states are passively steerable and which are not. And this is related to the concept of frustrated Hamiltonians, I don't have time to explain it. When it comes to active, you can overcome this and even still in the case of frustrated Hamiltonians.
This is true even for wave functions for of systems with high dimensions like 2-dimension and so on and so forth.
It would be a challenge. What? Tori code.
Okay, so then that sort of answers the second part of the question. I was
So you ask about unsteerable systems.
passively unsteerable.
Back to the steerable or unsteerable?
Unsteerable.
Unsteerable.
Yeah.
Toy code. There is a Dirac or Majorana SYK are unsteerable. Eisenberg antiferromagnet is unsteerable.
The 1D chain is unsteerable.
Yeah.
Can I say that if the target state has long range entanglement, then it will be very difficult to steer it lightly?
Yeah. So the point is this: with passive steering, you are absolutely right. One of the things we tried with the active steering was the so-called GHZ state or W states. So, for example, the state 00000 plus 11111 is a GHZ state, which involves long-range correlations or entanglement, and we showed at least a proof of concept that we can steer it with active steering.
So even for states with non-zero topological entanglement entropy?
This I don't know. Don't know. Very good question. Don't know.
Thanks.
Thanks. I had a very general question whether this kind of protocols, the last part of your talk, can be applied to systems which are interacting with an environment. So interacting with an environment and can decohere. So can you use some steering methods to preserve the state? So it's not like having a target state, but you are given a state and you want to preserve it. Is that possible with similar kind of?
The answer is absolutely yes. It's a very, very important question. So imagine the following. Imagine that I have a certain protocol that carries me or stabilizes me not towards a state, but towards a manifold. The simplest, I have a manifold which is defined by two independent vectors. So I go from somewhere and I end up at a point on this manifold. Now, what I can, so I have a certain vector in this manifold. Now, I can vary the my protocol adiabatically such that this state will be rotated, or if it involves two particles, I can braid two particles in this manifold. But the fact that I keep steering preserves me in this manifold, protects me in this manifold from other degrees of freedom away from this manifold. So I can do adiabatic manipulation on the background of constant steering. So the steering preserves me, and the adiabatic things will keep me with manipulations inside the space. So.
Yeah, questions.
Are there any experiments on, like, which have seen quantum steering? Are there any experiments which have?
Okay, so I mentioned the collaboration with the experimentalist. So one thing that we predicted was that a steering that implies a topological transition. Imagine that I have spin half, and I prepare it on the equator of the Bloch sphere. So now I perform a projective measurement direction very close to it. So with all probability, the spin will be projected here. And now I do it slightly away and so on. So I can drag the spin around. And when I finish it, it will describe winding number 1. If my measurement has strength 0, I can proceed with my measurement, the spin will remain unchanged. Total winding number 0. So it stands to reason, and this is indeed the case, that as I vary the strength of the measurement, I will have trajectories with winding 0 going to winding a 1. This is not topological yet, because this is a circle on the sphere. But I can do it for any spin with any, pointing on the Bloch sphere, and take the collection of the geometry of all possible initial states, and by controlling the strength of the measurement, I can have an envelope that wraps the entire Bloch sphere, which will involve a Chern number of +1 or -1, or if the measurement is weak enough, I will have an attempt of envelope which will start but go back, Chern number 0. So with this, we managed to convince our experimental friends working on superconducting qubits to do the experiment published, and our friends from quantum optics, it's about to be published. There is another steering protocol, again involving essentially qubit with cold ions on a different problem that is done. To do experiments on a many-body system is still a challenge.
Maybe some cold atom system.
Okay.
There are no further questions. Let's thank the speaker. Very nice.